Welcome to the lesson on the role of motors in battery electric vehicles. In this lesson, we will explore the fundamental differences between engines and motors and identify the various applications of motors in battery electric vehicles. We will analyze the impact of electric motors on vehicle design and weight and discuss how they contribute to the environmental benefits of BEVs. Finally, we will examine the future of transportation and the role that electric motors and BEVs will play in shaping it. Let us start off by describing an engine. An engine is a device that converts chemical energy into mechanical energy, with the most common type being the four-stroke internal combustion engine, ICE. In this engine, a mixture of fuel and air is combusted inside cylinders. The resulting expansion of hot gases pushes pistons, which in turn rotate the crankshaft, generating torque. This mechanical energy is then transferred through a transmission, also known as a gearbox, and ultimately to the wheels, propelling the vehicle forward. A four-stroke internal combustion engine operates through a cycle of four distinct strokes. During the intake stroke, the piston moves downward as the intake valve opens, allowing an air-fuel mixture to enter the cylinder. This is followed by the compression stroke, where the piston moves upward while both valves close, compressing the air-fuel mixture. The power stroke comes next, initiated by the spark plug igniting the compressed mixture. The resulting explosion pushes the piston down, generating power. Finally, in the exhaust stroke, the piston moves back up as the exhaust valve opens, expelling the burnt gases from the cylinder. This cycle repeats continuously, providing the mechanical energy that powers the vehicle. Now let us look at an electric motor. This is a device that converts electrical energy into mechanical energy, and it is used in a wide range of applications, including pumps, fans, and electric cars. The electric motor works on the principle of electromagnetic induction. It produces a consistent torque at any given speed, eliminating the need for a multi-speed transmission or gearbox, making it efficient and versatile in various applications. Motors come in various sizes and configurations, such as alternating current motors, direct current motors, and brushless motors, each with its own advantages and suitable applications. A comparison between an internal combustion engine and an electric motor used in vehicles is presented here. Engines, fueled by combustible fuels like gasoline or diesel, convert chemical energy into rotational mechanical energy, propelling the vehicle with power generated through combustion. They emit exhaust gases and pollutants, require regular maintenance, and have varied efficiency and performance levels. Motors, powered by electricity from batteries or the power grid, convert electrical energy directly into mechanical energy. They generally emit no pollutants directly, require less maintenance due to fewer moving parts, and offer instant torque delivery, especially at low speeds. While engines have a wider driving range but emit pollutants and contribute to air pollution, motors are quieter, have lower emissions at the point of use, and offer potentially lower operating costs over time, depending on charging infrastructure and electricity generation methods. Fuel stations are widespread and established, offering convenient access to traditional fuels like gasoline and diesel, while recharge stations for electric vehicles are steadily growing in number, aiming to provide accessible charging points for the increasing demand for electric vehicles. Let us now take a look at the various applications of electric motors in BEVs. Electric motors are the primary source of propulsion in BEVs. This propulsion system provides instant torque delivery, resulting in smooth and responsive acceleration. Electric motors in BEVs also function as generators during braking, converting kinetic energy back into electrical energy and storing it in the vehicle's battery. This regenerative braking system improves energy efficiency and extends the vehicle's driving range by capturing energy that would otherwise be lost as heat during traditional braking. Some of the other uses of motors in a BEV are comparable to the ones in a conventional vehicle. Electric power steering systems use electric motors to assist the driver in steering the vehicle. By applying variable amounts of assistive torque to the steering mechanism, electric motors enhance steering control and responsiveness, especially at low speeds and during parking maneuvers. Electric motors drive the compressors and fans in BEV air conditioning and heating systems, also termed climate control. These motors regulate the flow of refrigerant or air throughout the vehicle's interior, providing comfort to occupants while minimizing the vehicle's overall energy consumption compared to traditional engine-driven systems. The windshield wiper motor drives the wiper mechanism to clear rain, snow, or debris from the windshield. Electric motors drive the mechanisms responsible for operating power windows and adjustable seats in BEVs. Electric motors also power the coolant pumps and fans in BEV cooling systems, ensuring optimal operating temperatures for the vehicle's battery pack, electric motor, and other components. We will now explore the impact of electric motors on BEV design. Electric motors are significantly smaller and more compact than internal combustion engines because they have fewer moving parts and a simpler design. A typical electric motor consists primarily of a stator, rotor, and associated windings, while an ICE has numerous components like cylinders, pistons, crankshafts, camshafts, and valves, making it much larger and bulkier. This compact size of electric motors allows for greater design flexibility and efficient packaging within the vehicle. Automakers can strategically place the motors closer to the wheels or even within the wheel hubs, optimizing the use of available space and enabling more aerodynamic designs. The absence of a bulky engine block and traditional multi-gear transmission, as found in ICE vehicles, frees up significant space in the vehicle's front compartment. This space can be repurposed for additional storage or redesigned to improve crash protection and safety features. BEV designers can create more spacious and open cabin layouts, enhancing interior space and passenger comfort. The flat floor design, made possible by the placement of batteries beneath the cabin, further contributes to increased legroom and cargo capacity. The simplified packaging also reduces the number of components and complexity of the drivetrain, potentially leading to lower manufacturing costs and improved reliability in the long run. Modern electric vehicles boast significantly improved driving ranges compared to their predecessors, with many current models capable of traveling hundreds of miles on a single charge. As mentioned previously, in BEVs, the electric motors can be strategically placed lower in the vehicle, often near the wheels or under the floor. By positioning the heavy components like the motors and battery packs low in the vehicle, the overall center of gravity is significantly lowered. A lower center of gravity ensures that the vehicle's mass is closer to the ground, reducing the likelihood of rollovers and improving stability. The lower center of gravity also helps improve weight distribution in BEVs. With the ability to place motors near each wheel in some BEVs, the weight can be more evenly distributed across the vehicle's length and width. This even weight distribution improves traction, handling characteristics, and overall driving dynamics. Better weight distribution also contributes to reduced tire wear and improved energy efficiency, as the vehicle's mass is more evenly supported by the tires, reducing excessive load on any particular tire. The improved stability, handling, and reduced risk of rollovers resulting from a lower center of gravity is particularly important in emergency maneuvers or in situations where the vehicle needs to navigate tight turns or uneven terrain. Let us move on to the aerodynamic considerations of battery electric vehicles. BEVs, unlike conventional internal combustion engine vehicles, do not require a large engine compartment or many of the bulky components such as intake, exhaust, and cooling systems. This absence of a protruding engine bay and simplified drivetrain layout allows EV designers greater flexibility in shaping the vehicle's front end for improved aerodynamics. BEV designers can create smoother, more streamlined front-end designs with minimal protrusions or abrupt shape changes. This reduction in frontal area and smoother transitions can significantly reduce aerodynamic drag. Improved aerodynamics directly translates to reduced drag forces acting on the vehicle. Lower drag means that the electric motors need to expend less energy to overcome air resistance, resulting in increased range and better energy efficiency. Moreover, improved aerodynamics can also contribute to reduced wind noise, enhancing the overall driving experience and cabin quietness, which is already an advantage of BEVs due to their quieter electric motors. Next, we will explore some of the environmental benefits of using electric motors for propelling vehicles. Unlike internal combustion engines that rely on the combustion of fossil fuels, electric motors are powered by electricity stored in the vehicle's battery pack. Electric motors do not produce any tailpipe emissions during operation. There is no combustion process involved, eliminating the release of harmful pollutants such as carbon monoxide, nitrogen oxides, and particulate matter that are typically associated with the exhaust from gasoline or diesel engines. The absence of direct emissions from BEVs contributes to improved air quality, particularly in densely populated urban areas where air pollution levels can be alarmingly high. This not only benefits the environment, but also has positive impacts on public health by reducing exposure to harmful pollutants. Electric motors can convert a significantly higher percentage of the input energy, typically above 60%, into useful mechanical work for propelling the vehicle. In contrast, internal combustion engines have a much lower efficiency rate, with the rest of the energy being lost as waste heat and through inefficiencies in the combustion process. This improved energy efficiency of electric motors translates directly into lower energy consumption for a given amount of mechanical work output. As a result, BEVs require less energy to travel the same distance compared to their gasoline or diesel-powered counterparts. Lower energy consumption not only reduces the environmental impact associated with the electricity generation, but also extends the driving range of BEVs, making them more practical for daily use. The true environmental potential of electric vehicles lies in their ability to seamlessly integrate with renewable energy sources, enabling a transition towards a more sustainable transportation system. As the adoption of electric vehicles accelerates, transportation will increasingly rely on electricity generated from clean and renewable sources such as solar, wind, and hydroelectric power. This shift will be facilitated by the development of intelligent charging infrastructure that is integrated with smart grids and energy storage systems. These smart grids will allow for efficient energy management, enabling the storage of excess renewable energy during periods of high generation and the distribution of this stored energy to charge electric vehicles during periods of high demand. By harnessing the power of renewable energy sources and leveraging advanced energy management systems, the environmental impact of transportation can be significantly reduced, as electric vehicles will essentially be running on emissions-free and sustainable energy sources. This seamless integration of renewable energy and electric vehicles will not only mitigate greenhouse gas emissions, but also promote long-term sustainability and energy independence. Electric motors and BEVs offer a substantial benefit in reducing noise pollution, contributing to a more pleasant and livable environment, particularly in urban areas. Electric motors operate with significantly less noise due to their simpler design and lack of explosive combustion. As electric vehicles become more prevalent on the roads, the reduction in noise pollution will be especially noticeable in densely populated urban centers, where excessive noise from traditional vehicles can be a major source of disturbance and discomfort. Lower noise levels not only contribute to a better atmosphere, but also have positive impacts on overall quality of life and mental well-being. Let us now discuss the future of transportation, grouped into 5 categories. Widespread adoption of battery electric vehicles, emergence of autonomous driving technology, smart mobility solutions, renewable energy integration, and lightweight materials and aerodynamic designs. Widespread adoption of battery electric vehicles. Continuous advancements in battery technology, charging infrastructure, and cost reductions are driving the adoption of BEVs. Governments and automakers are setting ambitious targets for phasing out internal combustion engine vehicles. BEVs are becoming increasingly competitive in terms of performance, range, and affordability. Emergence of autonomous driving technology. Electric powertrains and advanced sensor technologies are enabling the development of autonomous driving capabilities. Autonomous electric vehicles have the potential to revolutionize transportation, improving safety and accessibility. Mass public transit offerings such as ride-sharing and mobility-as-a-service models could become more prevalent, changing vehicle ownership patterns. Smart mobility. Electric vehicles will be integrated with advanced connectivity features and smart mobility solutions such as real-time traffic updates, route optimization, predictive maintenance alerts, and over-the-air software updates. Vehicle-to-everything communication, such as vehicle-to-vehicle, vehicle-to-pedestrian, and vehicle-to-infrastructure communication, will enable efficient traffic management and improve safety. Seamless integration with public transportation and multimodal mobility solutions will enhance overall transportation efficiency. Renewable energy integration. Transportation will increasingly rely on renewable energy sources, such as solar, wind, and hydroelectric power. Charging infrastructure will be integrated with smart grids and energy storage systems for efficient energy management. This will further reduce the environmental impact of transportation and promote sustainability. Lightweight materials and aerodynamic designs. Battery electric vehicles will continue to incorporate lightweight materials and aerodynamic designs to maximize energy efficiency and range. Advanced manufacturing techniques and material science will enable innovative vehicle designs and structures. This will contribute to improved performance, reduced energy consumption, and lower operating costs. Let us now summarize what we have learned in this lesson. Electric motors convert electrical energy into mechanical energy for propulsion and various other functions in battery electric vehicles. The use of electric motors enables compact vehicle design, improved weight distribution, and increased interior space. BEVs equipped with electric motors produce zero direct emissions, contributing to better air quality. Additionally, electric motors allow for more aerodynamic vehicle designs, reducing drag as compared to internal combustion engine vehicles. BEVs, powered by renewable energy sources, can further reduce the carbon footprint. The future of transportation is set to include widespread BEV adoption, autonomous driving, and smart mobility solutions. Thank you.